Okay, so here's my limit that I'm looking at, and I've got this function over here, and we'd like to know, as x approaches 0, what does the y value of this expression approach? We want to solve this limit algebraically if possible. So step number 1, we're going to do that bar napkin idea. We're going to do some scratch work on the side, and we're going to check to see what happens if we plug in x equal to 0. In the numerator, we get 0 times sine of 0 plus 2 times sine of 0. And in the denominator, we have 0 squared plus 0. So numerator, sine of 0 is 0.
Oh, minus.
Oh, I have a minus. You're right, I do have a minus. Thank you. I think it was all zeros anyway. Thank you. In our numerator, we end up with 0 because sine of 0 is 0, and 0 times anything is 0. And in the denominator, we have 0 minus 0, which also is 0. Okay, so this tells us 0 over 0 tells us, okay, we might try doing some algebra work. Now, in our previous example, we only had sine x over x, and there wasn't any algebra that we could do it. So we had to back up and we had to use our graph to come up with a value of 1. But now we actually know that this limit value is true. So I might, in my mind, keep that around as handy knowledge, and we know that the limit as x approaches 0 of sine x over x is equal to 1. So I might put that in a thought bubble and remind myself. And so now I'd like to go back to our limit here and ask, is there anything we can do to factor? Okay, Aaron, you say this.
Yes, you can factor out sin x in the top and then x in the bottom.
Great, so we've got the limit as x goes to 0 of sine x times x plus 2. And in the bottom, we can factor out the x, and we're left with x minus 1. Okay. So now we've got this nice factored expression. What I notice about this is that even though I have factored things, I can't cancel anything. Not as it is right now, but what we do see is there's a sine x over x in there. And remember that idea with our limits that if we have the product of two functions, we can distribute the limit to each of those terms in the product. Okay? And so I can break this up as the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of x plus 2 over x minus 1. Now, I do have to be a little bit careful when I do this because, number one, I need to make sure that I, in fact, have two functions that are multiplied together, and I do. It is legitimate to say that sine of x over x is multiplied times x plus 2 over x minus 1. That's legitimate. Another thing we need to check is that when I split these two up, the product of these two functions, when I split it into their separate functions, that my limit is going to exist in each case. Now, I may not know that right away, so I have to tread carefully here for a minute. But once I split this up, this first limit immediately becomes what? Limit as x goes to 0 of sine x over x is exactly 1. And our second limit, the limit as x approaches 0 of x plus 2 over x minus 1, well, that limit, when I evaluate that limit, well, when I look at plugging in 0 in my denominator, I'm okay, because I no longer have 0 in the denominator. I also don't have a 0 in the numerator, which means I can distribute that limit to the top and the bottom, and I can immediately plug in that 0 in for x. And so I might as well just go ahead and plug that in, and I've got 1 times 0 plus 2 over 0 minus 1. And so we've got 1 times negative 2, which gives us a final limiting value of negative 2. So what this says is that if we were to graph this function, initially we'd have a hole in the graph at x equals 0. And if we want to fill in that hole, we would fill in that odd value of -2. All right, are there any questions on solving this limit algebraically?